10 million, the population of Sweden, also the amount of people suffering from Parkinson's worldwide. What causes this sickness? Parkinson's disease is a neurodegenerative disease characterized by chronic and progressive loss of neurons in the brain. During Parkinson's disease, a protein starts to misfold and form aggregates. These aggregates are thought to be the main contributor to disease progression and neuronal death. This protein is called alpha-synuclein. The most straightforward way of diagnosing this sickness would be to take a sample of brain tissue and scan it for the misfolded accumulated protein. Unfortunately, this would have some serious side effects for the patient. We need a method where we can look into the brain without cutting it open, like a PET scan. Antibodies can help with Parkinson's disease diagnosis. They are very specific to their target, like a key to its keyhole. Positron emission tomography, or PET, is a non-invasive technique that allows us to see what is happening in the brain in real time. The patient is injected with a radioactive tracer. The tracer binds to the target that we're interested in, like alpha-synuclein. The PET scanner then detects the radioactive decay from the tracer, which is bound to the target, and produces a 3D image of the location of the target. Unfortunately, there is currently no PET tracer for alpha-synuclein aggregates, and that's where we come in. With PET imaging, we could use a radio-labelled antibody binding to alpha-synuclein to get a picture of the pathology of Parkinson's disease. Several challenges arise when creating an antibody-based PET tracer for Parkinson's disease. Antibodies are big molecules and do not easily enter the brain. The brain is protected by a very restrictive barrier which does not let antibodies through. This barrier is called the blood-brain barrier. So how can we get the antibody into the brain to see if somebody has Parkinson's disease or not? To get the antibody into the brain, we use a method the ancient Greeks knew already, a Trojan horse, but in our case, a very small molecular Trojan horse. The blood-brain barrier contains proteins which carry large molecules across. Our molecular Trojan horse binds to one of these proteins, the transferrin receptor. We attach our molecular Trojan horse to our antibody. It binds to the transferrin receptor and is carried into the brain. Another challenge is that antibodies stay in the body for a very long time. This is an excellent characteristic for the original purpose of antibodies, to protect our body. However, this is not exactly what we want when designing a PET tracer, because then there is a radioactive molecule attached to the antibody. To solve this challenge, we can use a pre-targeting technique. In pre-targeting, a small molecule is attached to our antibody. This small molecule can quickly bind to its counterpart. The small molecule and counterpart are like two Lego blocks, which click together. Antibodies with this Lego block are injected into the patient, and after a few days, when the antibody has passed through the body and found its target, the counterpart, which has been radiolabeled, is injected. This method minimalizes the amount of radioactivity the patient is exposed to. It also increases the contrast of the image. This pre-targeting technique also has the benefit of creating a modular system, where a polymer with several Lego pieces is attached to the antibody. Increasing the number of Lego pieces gives us more flexibility. We can increase the number of radioactive molecules to enhance the PET signal.